All right, this jersey here is really going to be annoying, isn't it? Ooh, all right, just gonna pop against that. Okay. So folks, we kind of, like, in the previous lesson before this, no, that was the circle one. In the second lesson on length of a line, I kind of planted a little seed. You remember when we took the length of the 3 lines of that triangle in lesson 2 on length of a line, and we're like, oh, well, based on this information, it's got to be scalene or whatever it was, the type of triangle. And that was your very first taste of analytic geometry. It's basically, we're looking at 2-dimensional shapes on an XY plane, like on the Cartesian plane, and we kind of just use some algebra to either determine what type of shape, quadrilateral or triangle it might be, or maybe it's like, hey, this is a right triangle. Can you confirm that it's a right triangle? And it's like, well, how might we do that, right? To verify or even classify a shape, whenever we're given a shape, whether it's a triangle or quadrilateral, what we're going to do is basically just calculate the slopes of each line segment and also the lengths of each line segment. And then it says here, as well as the coordinates of the midpoint, which there are cool and exciting ways to do things with midpoints, but I think for right now, we're just going to calculate slopes and the length of the line segment. Now, let's recall, what do we remember about parallel lines? We kind of touched on this in Unit 1. What do parallel lines and their equations have in common? Yeah. Yes, the lines never meet, of course. But really, in high school, we're thinking they have the exact same slope. So we could say the slopes are equal. And you probably already know that, but it's good to kind of, oh yeah, I remember that. Now, how about perpendicular lines? We haven't really talked about perpendicular lines since the first week of school when we were reviewing some of the grade 9 stuff, but what do you remember about perpendicular lines? Yes, the slopes they're not the same or equal, they're the negative reciprocal of one another. The slopes are negative reciprocals. And that was a funny word we learned in grade 9. And it was either me or Mr. Todd, we broke it down. When we say negative, we really mean just change the sign. Yeah? If it's positive, the negative reciprocal is going to be negative. Or perhaps if it's negative, the negative reciprocal is going to be positive. Yeah? We just change the sign, and reciprocal kind of just means flip. So we're changing the sign and we're flipping the slope. So if we have a slope of, for example, m equals 2 over 3, for example. Yeah? The perpendicular slope, or perhaps we can even mark it like that, a little subscript of an upside down T, it looks like. The perpendicular slope would be negative 3 over 2. So we flip the fraction, of course, and we change its sign from positive to negative. Remember that? Also, the length of a line. Length of a line, we remember that. It's in our toolkit. We have the length of, for example, AB equals the square root, and the square root goes on for quite a while here, of x2 minus x1 squared plus y2 minus y1 squared. And we're very familiar with that. What happened to my little page down thingy? View, page extender, there you go. Oops. And lastly, who remembers how to calculate the slope between 2 points? Remember that? Slope, but sure, there's many ways to calculate slope, right? Change in y over the change in x, delta y, delta x, rise over run. But what was when you're given 2 points, Camille? Yeah. Yeah, we'll say the slope, and it's a lowercase m, equals y2 minus y1 over x2 minus x1. Now, do you remember when we talked about the change, the vertical change here, right? This we knew was vertical change. And this down here was horizontal change. When we talked about that, we kind of compared the vertical and horizontal change to something like the legs on the right triangle. So if we had like a line, right? This was down here, the horizontal change. This was the result of x2 minus x1, the length of that green line, yeah? And this vertical line is the vertical change, and it was the result of y2 minus y1, right? And that's kind of how we derived that length of the line formula, wasn't it? We took a squared plus b squared and made it equal to c squared, right? Sorry about that. Now, look what's in common here between these two formulas. What do you notice? Between the length of the line and the slope between 2 points. What do you notice about those two formulas? What do they have in common? Nick? That's right. They both have the change in x and the change in y. The change in x and the change in y. And that might be a really helpful thing to remember, as it'll be a pretty cool tool to use as we go on and do a bunch of calculations here. Now, let's also remember an equilateral triangle. How many equal side lengths does each have? Well, equilateral triangle has 3 equal side lengths. Sure you remember that? And of course, they're kind of denoted by these little ticks, these little tick marks. Tells us that they're all the same. And an isosceles triangle would have 2. And again, it's because we got the same tick marks here. In a scalene triangle, how many equal sides is each? It has 0 equal sides. And if you notice each side length, there's no little markings indicating that any side lengths are equal. And lastly, you might remember this, the area of a triangle, yeah? Area equals base times height divided by 2. Some of you might have seen it like that. Or if that's not something you're comfortable with, I know for sure, especially on EQAO, they like to give you this one here. Yeah? But either it's literally the exact same thing. Just whatever you're comfortable with. Half the base times the height. Okay. So far, so good. Now, it may have been a little while since we've looked at any types of quadrilaterals here. And I know triangle, coming out of grade 9, triangles, pretty good. They're pretty awesome. Now, if we're looking at this slide here is set up in a particular way with the parallelogram beside the rectangle on purpose and the rhombus beside the square on purpose. So, hey, how's it going? If we're looking at the side lengths of a parallelogram, how many, what do we know about the side lengths of a parallelogram? And I'm going to look, so 2 hash marks, 2 hash marks, 1 hash mark, and 1 hash mark. What does that tell us about the side lengths of a parallelogram? It might tell us that the opposite sides are equal in length. Now, parallel sides. Well, if you look here, we got a parallel line going this way with another parallel line, yeah. And also, well, there should be 2 here. So this and this other opposite side, it's going the same way as that side. So which sides are parallel? Well, again, we might be able to say, well, opposite sides are parallel. Now, are there any perpendicular sides in a parallelogram? I'm going to look at the, well, perpendicular really means that we're looking at the, is there any 90 degrees in there? Is there any 90 degrees? It doesn't actually look like there's any because we just have an X and an X and then a circle and a circle. It doesn't quite indicate 90 degree. A 90 degree, really what we're looking for is that box, right? That little 90 degree box. So we could say, well, there is none here. And then a little formula for the perimeter. Well, the perimeter of any quadrilateral can pretty much be 2 times the length plus the width, something like that. Or maybe it's just side plus side plus side plus side if you want. Or 2L plus 2W. There's many different ways to kind of look at it. Now, it's a parallelogram. You probably haven't seen one of those in a little while. Now, I kind of want to compare this to a rectangle. So a rectangle, side lengths, kind of the same idea, right? Like 1 hash mark, 1 hash mark, 2 hash marks, and 2 hash marks. So it shares the same property as a parallelogram, right? Opposites, we can again say opposite sides are equal. We're not shocked by that at all. Parallel sides? Well, yeah, absolutely. I know it doesn't say or show these little arrows here, but because we know that there's 90 degrees here and 90 degrees here, we can fully say with confidence that opposite sides are parallel. And so far, in both of these characteristics of a parallelogram and a rectangle, they're the exact same. Look, opposite sides are equal in length, opposite sides are equal in length. Okay, opposite sides are parallel, opposite sides are parallel. Okay, so far they have the exact same characteristics. Till we get to here. Yeah, perpendicular. You see any perpendicular lines? Yes. We for sure see them. You could say something like maybe the adjacent sides are perpendicular. Adjacent sides are perpendicular. And here we have the perimeter of this thing, of course. Oops. 2 times the length plus the width, sure. So a rectangle and a parallelogram have a lot of common characteristics with one another. The only difference is that a rectangle would have perpendicular adjacent sides, right? These little 90 degrees here. So far, so good. Okay. Now, kind of rhombus and a square. It's probably been a long time since we've seen a rhombus, but similar to how a parallelogram has common characteristics to a rectangle, a rhombus and a square also have common characteristics as well. So if we're looking at side lengths of a rhombus, notice we got 1 tick, 1 tick, and also 1 tick and 1 tick. Very similar to a square. Look at that. So we could say all sides are equal. And over here as well. Next, parallel sides. Oh yeah, check this out. This has got it's got the arrows for us here. Opposite sides are parallel. And for a square, it's the same idea. The opposite sides are parallel. So again, so far, they have common characteristics. They're the exact same shape so far in terms of what we're looking at until we get to this one right here. the perpendicular sides. A rhombus does not have any perpendicular sides, but a square certainly does. Yes. Adjacent sides are perpendicular. I can't fit the whole word perpendicular, so I'm just going to write perp. And if we're talking about perimeter of these things, since they both have all equal sides, you could say perimeter is equal to 4 times the length, or 4s. We like to use s. Or side plus side plus side plus side. Either way, perimeter, we know we're just adding up all of the side lengths on the outside, that is. All right. You might have not have been shocked by anything on this slide, but it is extremely important and crucial that we understand these types of quadrilaterals, because you're going to see next that it can be like, it can be the smallest, littlest thing when you're trying to classify one of these shapes, and that is because they share a lot of common characteristics. Okay. Oh, this graph, be careful, it counts by 5s, all right? It says a surveyor has marked the corners of a lot where a building is going to be constructed. The corners have coordinates P, Q, R, and S. Each unit represents 1 meter. Okay. So instead of writing units, we can write meters. The builder wants to know the perimeter. So, wants to know the perimeter of this thing. And also the shape. What type of shape is this? Now, because it has 4 corners, we know for sure it's going to be some sort of quadrilateral. So because sometimes it's really nice to just see this thing, right? -5, -5, right here, that's point P. Q is -30, +10. R is -5, +25. S is 20, 10. And with a straight edge, I'm going to go ahead and try my best to connect the dots the best I can here. Take a moment to connect those dots. Now, right off the hop here, what does it look like? Like, I know the graph isn't to scale, things like that. You know, it's made by human hand, so there's of course margin of error there. So, but we're pretty clever individuals in here. What might this be? Hey, what do you think, Nick? A rhombus? How come? Yeah. Oh yeah, R and P are on that. They both have that -5 there. Oh yeah. R and P are both at x equals -5. Rhombus for sure, I agree. But again, because it's graphed on a graph that might not be a perfect graph, because you know what happens when sometimes when I copy and paste graphs? Oh, I can't actually show you here. But you know, sometimes you can grab an image and you stretch it, and then it gets all pixely, and it gets all weird looking and things like that. So what that can do is kind of cloud our judgment a little bit based on what we see. So that's why we have algebra to kind of verify these types of things. Now, you say that all the sides look equal. Maybe it could also be a square based on that, right? All sides. Oh, okay, maybe not. Are, or they look equal. Who knows? Now, the first thing they want us to do here is they want the perimeter, which I think you already know what's going to happen. We're going to need to calculate the length of each line segment, for sure. Great. Now, what else is going to have to happen here is we're going to have to, at some point, prove that it's a rhombus, or maybe prove that it's a square. Now, when you're looking at proving whether it's a square or a rhombus, you can't just go off the side lengths, right? Because as we just talked about, if we go back a slide, a rhombus and a square both have all equal side lengths. So what we're going to have to do is not only calculate all the side lengths, we're going to have to do that for sure, but what we're also going to have to do is calculate the slope of each line. Now, when we calculate the slope of each line, if there are any negative reciprocals, yeah, there's 90-degree angles, and that means it's a square. Yeah? If there's no negative reciprocals, then we're in good shape. We know for sure that opposite sides are going to be parallel, right? We know that. They're going to be, should be the same and same, the same and same, yeah? But, hey, once you see those negative reciprocals, then it's game on, you know? You got to be really sharp on this stuff. And that's why we call it analytic geometry, because we're graphing these things, we're doing some algebra, and we're analyzing our findings here and making a call on what this might be. Okay. Tons of space here. Tons. We said we're going to be calculating the length. So the length of a line formula is something like AB, for example, equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And then we're also going to have to calculate the slope of each line, which is y2 minus y1 over x2 minus x1. Okay. So first, PQ. Now, really what we should be doing is writing the formula down for the first time every time here. But for the sake of space and fitting all of this algebra on a single slide, it might not happen, but we'll try. P, I like to write out the coordinate -5, and Q is -30, 10. Yeah? So in this box, perhaps we can do length. In this box, we'll do slope. x2 minus x1 squared plus y2 minus y1 squared. And I'm going to go up here and say, okay, x1, y1, x2, y2, PQ equals -30 minus -5 squared plus y2 10 minus -5 squared. PQ, -30 plus 5 be -25 plus 15 squared. Is that right? We confirmed? And we'll get something like, well, what you can actually do, honestly, is you can just put this in one shot. -25 squared plus 15 squared. But be careful with your brackets, okay? Because the square of a negative is always positive here. So it should be root 850. Is that right? Can I get some confirmation here? And we're looking at about 29.1, say, meters. 29.1 meters. Lovely. Now, slope. M equals y2 minus y1 over x2 minus x1. So we'll do 10 minus -5 over -30 minus -5. And I did that pretty quickly because I knew I was very careful over here. And I know that this is x2 minus x1. It's already written for me right here. I know that this is y2 minus y1. It's already written for me right here. So if you do one of them really quickly, the second one will go super fast. So we should have something like 15 over negative 25. Now what we should do is reduce this fraction to lowest terms and put the negative, if there is a negative, put it in the numerator. So we should have negative 3 over 5. Cool? Okay. 3 more to go. I know. QR, here we go. So now we have top and bottom here. So QR, Q, negative 30, 10, R, negative 5, 25. We got x1, y1, x2, y2. Now, we should write the formula for length of a line. Truly, we should. Negative 5 minus 30 squared and 25 minus 10 squared. Negative 5 plus 30, positive 25 squared plus 25 minus 10 is 15 squared. Well, that should be root 850, which should be 29.1. And we're not too shocked by that, because we thought rhombus, right? We were thinking rhombus. So we can now do maybe the slope of QR equals y2 minus y1 over x2 minus x1, which is 25 minus 10 over negative 5 minus negative 30. 25 minus 10 is 15 over positive 25 for sure. Positive 25? Yeah, agree. And this slope would be 3 over 5, but positive for sure. Yes? Positive for sure? Just to double check. And I can also look here. Okay? Have you noticed this part yet? Y2 minus y1? X2 minus x1? Yeah? RS. Oh, my favorite one. RS. R is negative 5, 25. S is 2010. RS equals y2 minus x1, y1, x2, y2. 20 minus negative 5 squared plus 10 minus 25. Oh yeah. 25 squared plus 15 squared. Root 850, about 29.1 meters. Now, really what you could do, if you see a shortcut, you're really clever. Y2 minus y1 over x2 minus x1. And notice how this is organized. I know there's boxes here, but like, you know, it's nice. 10 minus 25 over 20 minus negative 5. So this is going to be negative 15 over 25, and this is negative 3 over 5. And then PS. P is negative 5, negative 5. S is 20, comma 10. We have x1, y1, x2, y2. Here we go. PS equals the square root. And my square root goes from one side all the way to the other here. 20 minus negative 5 squared plus 10 minus negative 5 squared. Minus negative 5 is 25 squared plus 15 squared, root 850, 29.1 meters. Now, on this fourth one here, when you find these little shortcuts and things like that, they're great. I love them. I truly do. I wanted to use it since the very first one we did. But when you start using shortcuts, what I've noticed in the past, and even for myself sometimes, when I'm doing like a solution page to something, sometimes I'll mess things up. And I'll for example, grab this first one and put it as the numerator for the slope, and this one as the denominator for the slope, and now my slope is wrong, So are the shortcuts there? Yes, 1,000%. But shortcuts sometimes can lead to some error unless you're extremely, extremely cautious. Why did that go so much? Okay, m equals y2. 10 minus negative 5 over 20 minus negative 5, which is 15 over positive 25, which is 3 over 5. Now, that is a ton of work. I know. I'm with you. Now, what might be what some of you are probably thinking, because you've been trained so well, is, for example, see QR. Let's have a look at just, let's do PQ. Or no, whatever. QR is right in front of me. QR. Yeah? Lovely line. Slope is 3 over 5, or we have the numbers 15 and 25. They come up all the time here, right? 15 and 25. QR. If we draw the right triangle, yes? What's the vertical change? Or perhaps y2 minus y1? 1, 2, 3. 3 boxes, I know, but each box counts as 5. So this is 15. Yeah? And then 5, 10, 15, 20, 25 across this way. So if we're talking about slope of this line, yeah, rise over run. 15 over 25. And look at this. It's exactly what we got. 15 over 25. And then we reduced it to 3 over 5 because that's what we do with fractions. We put them in lowest terms. Also, what's super great about right triangles is that if we wanted to calculate the length of QR, we could just use this right triangle, use the Pythagorean theorem, c squared equals a squared plus b squared, and off we go. Yeah, you see? If you wanted to use it that way, absolutely. Absolutely. In fact, I highly encourage any question you come across that requires you to verify a shape or classify a shape, draw it. Draw it the best you can. The only time this method here of drawing the right triangle comes out to be nasty is when the coordinates are not whole numbers or are not like integers. When they start becoming, okay, negative 2.8, and some. Will that come up? Probably not a whole lot, but it might. But if ever you're given a chance, do you see the convenience in drawing here? I have tons and tons and tons of stickies. If you wanted to draw anything in your notes, in your homework, whatever it might be, here they are. These little graph pads. You've seen them before? You can draw, so many good things here. And if you needed anything to, if you needed little graphs, I have tons of little graphs here with grid lines, with Cartesian plane already there. And we have a printer in the classroom, which no one knows about, so don't tell anyone. And then we can just print it off, cut them out, and off we go. We're going to be in great shape. Cool? Okay. Now, we have a ton of information here, almost information overload. But the first thing I want to do is have a look at the lengths. 29.1, 29.1, where are we? They're all 29.1, 29.1, 29.1, 29.1. All of the side lengths are equal, which means it's either a square or a rhombus. Agreed? Okay. Let's have a look now at the slopes. Negative 3 over 5. Negative 3 over 5. Opposite sides are parallel. Positive 3 over 5. Positive 3 over 5. Those opposite sides are parallel. And that's great. Now, are there any perpendicular slopes here? No, there's not. It's so close though, right? One's positive, one's negative, but it's not a negative reciprocal. Yeah? So be cautious of that. That could be a little tricky. So so maybe we should write that down. All sides are 29.1 meters in length. So that's the sides. Now the slopes. What can we say? What do we say? Slopes of opposite sides are equal? Whoops. Start off with the word slopes. Slopes of opposite sides are equal, which means that they're parallel lines, which we know from Unit 1, of course, and even Grade 9. And we can say there are no negative reciprocals, meaning no 90 degrees. That's all of the information that we that we spent an hour calculating. We did it the long way so that you can appreciate the short way, honestly. So since the sides, please, okay. Since the opposite sides are parallel, and all side lengths are equal, PQRS is what type of shape? Rhombus. It was almost a square, but there's no right angles, right? That's a good therefore statement. Maybe we should even put the word little therefore, yeah? So we classified the shape as a rhombus. Now the perimeter of this thing is, well, P equals 4 times the length, which is really, I put P equals in front of perimeter equals. Sweet. 4 times the length. So we say perimeter equals 4 times 29.1. Going right to my calculator that I don't have. Oh, there it is. 116. P equals 116.4 meters. Therefore, the building lot is a rhombus. its perimeter measures about, and we say about because we've rounded some things in there, 116.4 meters. Folks, questions about that? Slope and length, slope and length, slope and length. It's pretty much all it is. Given the opportunity, given the opportunity, we are going to graph this thing. We are going to use our prior knowledge, our existing knowledge. Life will be great. Okay. We got one more here. A little bit, it's got some more to it than that previous one. Tony, of course they used the name Tony, is constructing a patterned concrete patio, of course. My Uncle Tony would be so proud. Tony is constructing a patterned concrete patio that is in the shape of an isosceles triangle. Oh, they tell us. They say, hey, look, it's an isosceles triangle, and what we remember is that two sides are going to be equal here. As requested by his client, on his plan, the vertices of the triangle are at 2, 1, 5, 7, and 8, 4. Each unit represents 1 meter. Lovely. Confirm that the plan shows an isosceles triangle, and then calculate the area of the patio. And that right there will be interesting. So, confirm that the plan shows an isosceles. Let's graph this thing. 2, 1, 2, 1. That's P. 5, 7. That's Q. R is 8, 4, R. Wow. Can someone put a mental note on Mystery Acquisition to get a new graph for this slide if we're only in quadrant 2 here? Quadrant 1. And of course, we're going to connect the best we can here. P, Q, R, back to P. Now, because we have it on a graph, and graphs are so lovely, aren't they? When we're talking about, we're going to be doing length. Length of, we're going to go PQ, length of QR, and at some point, length of RP. So maybe, let's first see what this is going to, maybe here. Now we know we have that wonderful length formula. It is great. Please don't get me wrong. We love the length formula. But, right, like you're like, okay, yeah, I know. PQ. What do we got? Are we counting by ones on the graph? We are 1, 2, 3, 4, 5, 6. By 1, 2, 3. Okay, so if we wanted the length of line segment PQ, you would say C squared equals A squared plus B squared. C squared equals 6 squared plus 3 squared, which is 36 plus 9, which is 45. We take the root of each side. Root 45 has got to be like 6.8 or something. Square root 45, 6.7. Oh. 6.7 meters. So maybe even on the graph, we can go in here and say 6.7 meters. I like to do that, but I also don't want to make a mess of my graph, but I do like to know what's going on in there, for sure. Okay, QR, not the code, the line segment. We got 1, 2, 3. 3 by 3. C squared equals A squared plus B squared. C squared equals essentially 9 plus 9, which is 18. And we take the square root of each side to probably get a little bit more than 4. Let's say 4.3. Let's say 4.3. Square root of 18. 4.2. See, I was going to go 4.2. I go right to the diagram. 4.2 meters. All right, let's grab green here. Let's use the primary colors today. 3. 1, 2, 3, 4, 5, 6. 6. Oh, we're not shocked by that. They say isosceles triangle. We say no prob bob. A squared plus b squared. We got 3 squared plus 6 squared, which we're showing our work here. 45. We root each side, and again, it's going to be 6.7 meters. We're not shocked by that at all. So, does this show an isosceles triangle? Yeah, I'm getting some nods. Yes. And how do you know that? How do you know? You're right. It does. But how do you know? Carolina? Lovely. So for part A, we'll say, therefore, PQR is isosceles. I'm going to spell that wrong. Isosceles. Because we'll say PQ and RP are equal in length. And that's not too shabby, right? Not too shabby at all. Oh, I forgot to go 6.7. 6.7. Okay. Now it wants us to calculate the area of this thing, which is a little strange, don't you think? That's kind of tough, because our whole lives we've been given triangles, like let's just say it was scalene, for example, right? And they give us this dotted length, right? Because it's base. Geez, let me get some corners here. It's base times height divided by 2, right? And we always have that. Does anyone know what that vertical length is called there on the height? What's another word for that height? You know what it's called? It starts with an A. Planes use it. Pilots use that word. It's called the altitude. It's the altitude of the triangle. So base times height divided by 2. What are we to do in this sort of scenario? Does anyone have maybe any ideas? What do you think? Divide. Now, when you say the base, you're talking about QR, the shorter side. So you want to divide that by 2. So it's about 2.1. Okay. And then? Okay, I like it. I do. Mr. O'Sullivan?
Do you have any more kids in here?
Could there be any more boards?
Board? They know board.
It's hard to judge. Actually, might be some. Might probably board.
Did I do board? No, man. You're math please. I got faith in you. Just question. Good question. What's your question?
Black.
All right.
I don't have an on-call today, so anything you need, let me know.
I'll just come down.
Okay, I gotta write that somewhere so I don't forget. Can you send me remind me?
Yeah, I was just doing that a lot better. Oh, what's going on? Does not want to talk to you?
Sometimes I feel like I'm teaching online, but in person.
Oh.
You know what I mean?
Is that because you guys are like mesmerized by his lessons?
No, it's because they know exactly what to do and they're like, hurry up.
Hurry
do
up,
my
yeah.
work.
Oh, okay. That's a good feeling. Okay. Take care.
Okay.
Yeah, I think you're a good person. You need to stay on.
That's all that matters, I guess.
We'll have to talk the time later on.
Last period, right?
Last year.
Yeah. So, Ryder says to take half of this base, which would be approximately 2.1, yeah, and then use the Pythagorean theorem to solve for the non-hypotenuse side, which is absolutely right. You're totally spot on. And a lot of us might take that approach, But I do want to show you another approach to this, because this approach might work in other types of shapes. When you say cut that base in half, what we could maybe do is get the midpoint. This is going to sound a little weird. We get the midpoint. X1 plus X2 over 2, Y1 plus Y2 over 2. This is for coordinate QR, or line segment QR. So we'll say Q and R, X1, Y1, X2, Y2, and then it's like 5 plus 8 over 2, 7 plus 4 over 2. And folks, notice that I'm writing midpoint of QR equals bracket, bracket, midpoint of QR. Because as I mark those things, these assignments that roll in here, some of us did not do that, which is fine, but I just want to correct it on there. Not take marks off, but correct it so that come test time, you know exactly what to do here. 13, is that what it is? 13 over 2? And then we got 11 over 2. Just 6.5, hello? 6.5, comma, 5.5. 6.5, 5.5. That actually looks pretty spot on there, the midpoint. Now I don't want to discredit Ryder's idea because it's totally spot on. You know, take half of the base and this and that. But assuming some measurements might be missing at some point, if we wanted the length of this P to the midpoint of QR, what we could do is now solve for the length using the length formula. So we'll say from the midpoint of QR to P equals, and we're going to use our formula here, x2 minus x1 squared. So what is point P? Where is point P? It looks like it's 2, 1. I'm just going to write that down here just so I remember. It's 2, 1. Is it 2, 1? Yeah. So x2, let's say 6.5 minus x1 squared plus y2 minus y1 squared. .5 squared plus 4.5 squared. Here's my calculator. Here we go. 4.5 squared is that. So we should have 40.5, but square root of that, which should be just above 6 here, 6.3? 6.36, so maybe 6.4 meters. And that actually seems quite fitting because it's less than the hypotenuse here. So that works out great. So now that we have the altitude of this triangle, we can go ahead and just solve for the area. So area equals base times height divided by 2. Area equals 4.2 times, we now know that that's 6.4 divided by 2. 6.4 times 4.2 divided by 2. 13.44 meters squared. So now we can go ahead and put our therefore statement and say something like, therefore, the area is 13.44 meters squared. We say meters squared for sure because we're talking area here. Okay. So on your sheet, it doesn't actually have this, but please mark this in because it is on the front page though. We're doing 1 to 4, but only 4A. Okay. Hey, how's it going? Only 4A, because I think there's a 4B as well. I don't want you to do 4B. And we got here 7, 8, 11, and 12. And again, if you have the chance to graph these types of things, please do so. Please do so. If you need stickies or anything like that, please let me know. Wow, I went right to the wire, folks. Sorry about that. Hey.
The way you got the area, that works on every single type of.
See, that'll work for a scalene every type of shape.
The way I was thinking is that you calculate the area of the, if you made a